So in chapter 1-2, we asked the question, what is a function? Well, it's simply just a relationship or pairing between two things. That's it. So as an example, we have Panutas. He is employed. He has a summer job. He's been working hard during the break. And Panutas has a summer job, and from that he earns 150 baht per hour. I know he should be paid a lot more than that, but let's just go with that for the example. So he makes 150 baht per hour. So his total weekly pay in baht, is going to be given by, well, pause and try and write the formula yourself for his pay. Right, it's going to be pay, let's just use P for the variable, is equal to 150 times H. Every hour that he works, he gets 150 baht, so we multiply the hours by 150. So H is going to be the number of hours that he works. If in a given week he works, say, 3 hours, then he would make 450 baht. Okay, so we can represent this function with a table. So we'll put the hours in the first row of the table and the pay in the second row, and we'll just write a couple of values. So if he works 1 hour, he gets 150. He works 2 hours, he gets 300, and so on and so forth. We have these different examples, and what we're seeing is we put in the hours and we get out the pay. And so that's the idea of the function, is it relates these two things, hour and pay. Right? So hour and pay, H and P in this equation or formula are considered variables because they can change. The 150, how much he gets paid per hour, that's not going to change. That's constant. But P and H are the variables. P we're going to call the dependent variable. In any vocabulary, I'll underline in red to kind of help highlight it. P is called the dependent variable because his pay depends on how many hours he works, right? So if he works more hours, he's going to get more pay. So P we're going to call the dependent variable because it depends on H. Well, H, the hours, that is independent, meaning Panutas can choose however many hours he wants to work, right? If he wants to work 1, that's great. But I know he's not lazy like that. He'll probably work, 40 hours, right? But the idea is that it's independent. He can choose how many hours. So H would be the independent variable. He chooses how many hours he works, and then out comes, you put it in the formula and you get pay, P. Okay. So I know this is kind of like a simple example of a function, but just want to use this example to highlight what the main idea of a function in the two parts of it, the variable, the independent variable, what you put in, and the dependent variable, what you get out. But let's look at the definition of a function. So a function, again, underlined in red for vocabulary, is just simply a pairing between the two variables. So just like you can represent the function in the table, you have the hours, and you're going to pair each hour. It's going to have a partner, right? The pay. You put in the hours, you get out the pay. The one thing about a function, and I always got confused with this in high school, it wasn't until much later that I kind of understood this part. There's one piece that makes a function different from a relation. A relation is just a pairing between two things, but the function, there's this key piece. The first variable is going to pair with exactly one value of the second variable, or what you get out. So I think this makes more sense if we can look at an example. So, well, just to finish off the first example, we would say P equals 150 times H. That is an example. We say P is a function of H because P depends on H, so it's a function of H. You can replace function with depends on, basically. So if you think about a function like a box, like a machine box, you put in the pay, not the pay, you put in the hours, H, throw that into the box crunches it, boop, beep, boop, 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 and then spits out the pay, P. So that's how you can think of it. So if that helps, is like a box that you put something in and then you get something out. That's all a function is. So we put in Panutas's time, his hours, and he gets out that sack of bot right there. Okay. So this next example I'm going to try and use to show the part about how a function has to have exactly, for every input, it has to have just one output. So I'm going to try and illustrate it with this example. So let's look at another function. Actually, I can't say function yet. We don't know it's a function. Relation between a year, y, we'll call the variable year for y, and the percent, p, of public high schools that have a computer for the students to use. Right? Okay. So we'll write this function as a table. You can represent, I keep saying function, but we don't know it's a function yet. A relation. We're going to write this relation in a table. We're going to do plenty of relations with graphs as well. Okay. There's many ways you can represent a relation. So we'll have the years going back to the 80s. 1981, 83, 85, 87, and 1989, and 1991. So in 1981, that was when computers were first starting to be made, so not many had it. 42.7% of high schools had it. And then Steve Jobs invented the Apple personal computer, and it became much cheaper and easier to get computers. So in 1983, we jumped up to 86.1% of high schools have computers, and it quickly got adapted so that we increased the amount of schools that have computers, and in 1987, 1989, it happened to be the same, 99.1%. It's hard to believe that not a single high school added computers, but let's just go with it. Okay, between 1987 and 1989, but I need to have those numbers the same to make this point. Is P a function of Y? Yes, because for every Y, every year, there's only going to be one output, 1%. So for example, if I put in 1987 as my input, I know I get 99.1% out. But is Y a function of P? Go ahead and stop and think. Well, no, it's not, because remember, for Y to be a function of P, that means for every P percent of high school, I need to know exactly what year that partners up with. And if I say, hey, the percent of high schools that have computer is 99.1, tell me what year that is. Well, you have two choices, 1987 or 1989. You don't know which one you want out. And that's the thing. A function has to know where it's going. It has to know which output you want. So if you give the input of 99.1, it's like, do you want 1987 or do you want 1989? And it can't ask that question. That's a relation, sure, but it's not a function. So hopefully that example helps you understand that. And if not, you'll be the same as me that didn't understand functions in high school. So don't feel bad. All right. Two things about the function is going to be the domain and range. By the way, if anything in the video is confusing, just ask me, send me a message, ask me in class, ask a friend. All right, so we talk about domain and range of a function a lot. So the domain is going to be just the set of values you can put into the function. In other words, what numbers can you put into the independent variable, right? So at first you might say, well, wouldn't it be any number? But we're going to see some functions where you can't put in any number because you're going to get something undefined. For example, if I have y equal 3x plus 6, I want to know what x's I can put in here. Well, any, right? Any number you can put in for x and you're going to get something out for y. Spoiler alert, if you have something like y equal 3 divided by x, think about what you might not be able to put in. I'm not going to spoil it for you, but think about that. The range is going to be the set of values you get out from the function, right? So it's going to be the values of the dependent variable. In this case, like if your function is y equals some, function of x like we have here, then, the range is going to be what y values come out. And in this simple example here, you're going to be able to get any y value you want. So it's all numbers for domain and range. Well, let's look at another example. We're going to have to find the domain and range for this function. So the domain is the inputs, right? What can we put in? So y is the inputs, the years. So we're just going to write those down. It's a little tedious. No wonder everyone hates math. But I write down all the numbers, the years I can put in. That's my domain. The range, pause and think about what it is. Yep. It's the outputs, right? And there are 5 possible outputs. You don't need to rewrite 99.1 just because it comes just because it shows up twice. So you just write all the possible ranges that you get out. Since that's our answer, we're going to highlight it in rainbow, just to make, hey, Ajan, here's my answer. Thank you. You're correct. Okay. Now, let's go to, so we've talked about domain and range. The last thing I want to cover in this video has to do with the sets of numbers. And when I first taught this class, Apisada, who you may remember from last year, grade 12, asked me a great question, which is, why do we have to know about the sets of numbers? I didn't have a good answer for her at the time because I couldn't really think of a reason. But what I've kind of come to the conclusion is, if you know these words and what they mean, you're just able to communicate more efficiently and quickly. Like you can tell someone, hey, the domain is rational numbers, and the person that knows these is going to know right away that, oh, you mean like a fraction, right? So we'll just go through them. The natural numbers is 1, 2, 3, 4, 5, 6. The counting numbers, we have used these as humans since 50,000 years ago, basically. And did you know chimpanzees and chickens can also count and use the natural numbers? Then it took us like 50,000 years to come up with the idea of 0, and that's the whole numbers. We add 0 into it. And India was the kind of the first place that used 0, like way back, like 2,000 years ago. And then integers, the idea of negative numbers, that came from China about like 1,800 years ago, because the Chinese merchants were recording money transactions and debt, and they were saying, like, you owe me, 3, whatever they were using for their currency, and so they would write -3, and that's how we have the integers. It includes everything above it, like the whole numbers, 1, 2, 3, 4, 5, 6, so on and so on, 0, and then the negative numbers as well. And then we came up with the rational numbers. I don't know when we came up with these, but they're basically numbers that you can write as fractions where the top and bottom is integer, and the bottom can't be 0 because we don't know how to divide by 0 yet. If someone figures it out, let me know. We can go win $1 million math prize. I'll split it with you, 50-50. No, just kidding. If you figure it out, go get the money yourself. Don't share it with anyone. So then the last one is the real numbers. And by the way, these sets of numbers like get bigger and bigger, right? Like all the numbers above, all the rational numbers, integers, whole numbers, natural numbers, they're all real numbers. And real numbers are anything that can be represented by a decimal. So like 0, 1, but that's boring. -7, stuff like 2/3, because you can write it as 0.666666. It can be a repeating decimal. It's fine. As long as it can be written as a decimal, it's a real number. So 2.34. Pi is another example, yum, because you can write it as a decimal, 3.1456, and it doesn't repeat and it goes on forever, but it's still a decimal. And so is square root of 2, which is like, 1.41, I think, and so on and so forth. Okay, so the thing is, if you know these sets of numbers, it helps you, like I said, with a lot of questions that are going to refer to these types of numbers. And for example, you might get questions about domain and range. So let's look at a quick function. Area of a circle, area equals pi r squared. You know that from, your 10th grade class, your geometry. Is area a function of the radius r? Well, pause and think about it. Is it for every r, are you only going to get one a? Yes, you are. You put in any radius and you know exactly what area is going to come out. There's no question what it's going to be. You just have to calculate it, so it is a function. And then since a is a function, the area is a function, the area of a circle is a function of the radius, let's get the domain and range. Find the domain and range. So pause the video here, think about it, and check and see if you're right. Yep, I knew it. You got it. The domain is going to be all the positive real numbers because it doesn't make sense to put in like a -2 radius, right? If our units is centimeters, let's say -2 centimeters, that doesn't make sense for the radius. So the domain is going to be just the positive real numbers. And the range, what's going to come out of this? Well, if we only put in positive numbers for the radius, if you think about it, the lowest thing you can put in would be 0 and the radius would be 0. You're not going to get a negative area. So again, the range is the same thing. Positive real numbers, highlight it, and good.